Hello, everyone. I'll just be making a quick video here. We had gone over this problem, number 17 from class, and we didn't get through part A. And I looked back over it, and I understand now why we weren't able to get to where we thought we could. So I thought I'd just go back over that. It's a good example of it's a good example of whoops, sorry everybody. There we go. Um, it's a good example of how you can chain these power functions together and sort of make a lot of meaning without having a lot of numbers. So yeah, we'll just go through that. All right. Pop that up a little bigger. Okay, yeah, so here's the kind of givens in this problem. And the issue in class was that we forgot to, oops. The issue in class was that we forgot to use this bit of information. So we're actually given two equations. So whenever you read V, or whenever you read something is directly proportional, that's telling you that V can be determined using a power function. And the power function is going to look like this. So L is going to be the variable, and it's proportional to the square root. So we're going to have a constant of proportionality K, and then that's going to be multiplied by the square root of L. So that's where that piece of information comes. We can say V is a function of L, and that function is the square root function. Okay. T was defined in the problem as this ratio. L divided by V, the wavelength divided by the velocity. And so the idea is we need to combine these two to show that T is proportional to the square root of L. Another way to write that would be T is a function of L, and that function is some constant K times the square root of L. So let's run with it. What do we know? And how we're going to do this? Via substitution. That's the method here. Okay, so first let's write down our function for T. The time between waves is L divided by V. But V is also a function of L. So how can I put these two things together? Well, let's use what we know about V in terms of L here. So I'm just going to plug that in for V. What I get is that T is the same thing as K times the square root of L. And that simplifies to 1 over K times the square root of L, using our exponent rules there, converting this to a 1/2 power down here. Now, is that a proportional function? What do we do if it's 1 over K instead of K? Well, this gets philosophical, right? The whole idea is that we have some number times our variable to some power. So isn't 1 over K some number? Certainly it is. So we can actually just redefine this as K root L. If you like, we could call it something different. A number A times the square root of L. And then we'd have this relationship over here where A was 1 over K from our original directly proportional equation. So there you have it. That's why T turns out to be directly proportional to L to the 1/2 power, or the square root of L. For part B, just to go over that so you have something to work with. So if we've discovered that T is some K times the square root of L, and for a certain L, that equals 3 seconds. For some factor a times L, that equals 6 seconds. And the idea is, what's that factor? Well, these things are equal, and these things are equal, so I can divide their sides, and the ratios will still be equal. So I'm going to shorten the steps a little bit by dividing this way. And my k's cancel, my square roots of L cancel, and this becomes 2. So I end up with the square root of a is 2, or a equals 4. So that's how that problem goes, guys. Sorry for the confusion in class. I hope that cleared some things up, and I'll be coming back at you with a shapes of power functions video. Hope you have a good day.